Newton's method, or sometimes called the Newton-Raphson method, is a numerical method to find zeros of a function. Here's the main idea. Here is the graph of the function y equals fx. First, we are going to guess a zero at the point x sub 1. Assume that we are guessing that this is a zero of the function. We are going now to draw a tangent line to the graph of the function at x sub 1. This line is intersecting the x-axis. The x-intercept of the tangent line is now going to be the new x. We are calling it x sub 2. We are now drawing a tangent line to the graph of the function at x sub 2. This tangent line crosses the x-axis at x sub 3. We are going to repeat, and we are going to stop when the difference between the x's is good enough, depending on the accuracy that is required. Assume that we need to solve the equation x cubed plus 2x to the power of 2 plus x minus 5 equals to 0. We are going to create a function out of this equation. Now you can see that solving the equation is equivalent to finding the zeros of the function. Please note that the above is just an example to illustrate Newton's method. It can be solved explicitly if desired. There is a way to solve cubic polynomial, but it's very unpleasant. Here's the graph of the function. And here is the zero. We can see that the zero is located more or less between 1 and 1.5. So if we want to do something more accurate than that, we are going to use Newton's method. Because the solution is between 1 and 1.5, we are going to choose a number in the interval between 1 and 1.5 to be the first guess for the x. We are going to take x sub 1 to be just 1. X sub 2 is going to be the zero of the linear approximation of f about x sub 1, which equals 1. I would like to recall that the linear approximation, also called the tangent approximation of a differential function fx at x equals a, is given by f of a plus f prime of a times x minus a. In our case, a equals x sub 1 or just 1. Let's substitute. We will replace x sub 1 by 1 and we get that. We are differentiating the function fx. We will substitute 1 to get f prime of 1 equals 8. And we will substitute 1 in the function to get that f of 1 equals to negative 1. And we get that. For our specific x sub 2, f of x sub 2 can be approximated by negative 1 plus 8 times x sub 2 minus 1. Here is the meaning of this equation. Y equals negative 1 plus 8 times x minus 1 is the equation of the tangent line to the curve at x sub 1, which equals to 1. In order to find a better approximation for x sub 1, we have to find the intersection of this line with the x-axis. I would like this to be 0 at x sub 2. And I will get the next better approximation at x sub 2. This is also the intersection of the line that is above with the x-axis. Solving is always easy. This is just a linear equation. And we get that x sub 2 equals to 1.125. Here is a better approximation. Now I would like to refine that. I'm going to repeat the process to get x sub 3. First I'm going to find the tangent line, but now the approximation is about a equals x sub 2. Here is the linear approximation. We get that. Now I would like to find when this line is intersecting the x-axis. So I would like this to be 0, and the solution is x sub 3. It's exactly when this line is intersecting the x-axis. This process can really continue for a very long time. In general, the next value of x is going to be just the intercept of the line that is given by y equals f of x, the one before, plus f prime of the x before, times x minus the x before. Or you can realize again as what we did is we every time find the 0 of the linear approximation using the previous value of the x. Let's magnify that. We started with our first value of x1 to be 1. Here's a tangent line, and here's the equation of the tangent line. The 0 of this tangent line was x sub 2. Then again, we found the tangent line to the graph of the function at the value of x2, and the intersection, this line with the x-axis, was x3. And we can continue doing this many times. Here's x4, and so forth. We are going to use this to find x sub n written as an expression of x of n minus 1, which means that we would like to express any value of x as a function of the previous x. First, we know that we have to solve this to 0, and x sub n is the solution. So let's do that. We get that, and then we get that, and that, which applies that. And we conclude that x sub n equals to x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. Newton's method is also sometimes called the Newton-Raphson method. First we guess 0 at x1. Then we draw a tangent line at x1. If this is the graph of the function and this is x1, here is the tangent line, and the equation of the tangent line is this. The x-intercept of the tangent line is the new value of the x, which is x2 now. Here's x2. Observe the coordinates of this one. The x-coordinate is x2 and the y-coordinate is 0. Let's substitute this in the equation of the line. Y is 0 and x is x sub 2. And we get that. Now let's try to solve for x sub 2. It's a linear equation. It's always easy to find out. And we get that x sub 2 equals x1 minus f of x1 over f prime of x1. As you can see, this is exactly what we got before in general, that x sub n equals x n minus 1 minus f of x n minus 1 over f prime x minus 1. When we repeat the process, we will get the following x's. Again tangent line, and again the x-intercept. Be careful, the choice of the first one is very important. If it is wrong, the values of the x will not converge to a solution. For example, let's say that the function is x cubed minus 3x minus 6, and let's assume that we choose x1 to be 1. We will use this, and let's find the second one using Newton's method. We get that x2 equals x1 minus f of x1 over f prime of x1. But in our case, what happens if we substitute 1? We get 0 at the denominator. A better choice will be to take x equals 2. But for x equals 1, we're stuck and it really doesn't work.